robotics in general and in robotic intelligence. You can tell I prepared.
Yeah, I can just look behind you.
Yeah, pretty much. So, we're still waiting on pizza, and at this point, enjoy the show.
Okay, so real quick, when the pizza comes, you guys eat after it? You guys eat during it or before?
During.
Okay, so we can take a quick break. I don't want to deny you of your pizza, your gourmet lunch. Okay, so I'm going to bring I need a couple volunteers, because what we're going to do is I wrote some very simple code on these little Mindstorm robots, and yes, I do realize these are somewhat antiquated. They run a little 8-bit microcontroller in here, but it does the job, which is kind of what we're going to talk about. What I'm going to do is have you guys, if it starts to, they run amok, you just kind of send them back along their way. I'm just going to randomly put them out there. And as you start to see these things interoperate, go ahead and tell me what you think's going on. That was starting to get away. You might want to go chase them.
Make a sensor setup.
So when you saw one of these robots running around, you really didn't look like much, did it? Just like a robot wandering around. But when we see 5 of them, when we see maybe 10 of them, what comes to your mind right away?
Swarm of bees.
A swarm of bees, some bugs.
Tripping hazard.
Tripping hazards. Hey, OSHA is not involved with this. They look like they're just menial animals foraging around, don't they? Now it turns out, if we looked at them long enough, we would start to ascribe behaviors and personalities to them. It's our natural human instinct to do that.
Like Wilson the volleyball.
Exactly. The Wilson volleyball. So these guys don't play volleyball, but I don't think they ought to. Are they very smart? No. But it turns out the behavior to do this is rather trivial. So now that we've got that kind of in our mind, do you all do me a favor, hit the red button, go turn them off.
Are they mapping out walls?
Yeah. What's that?
Are they mapping walls or buried?
Potentially they could. We're going to talk about that. I got a quick little video on that way too. So
they're checking if they bump and they back up.
clearly, these robots, when you look at them as an individual, they're not terribly intelligent. But the question remains is, could a set of simple behaviors exhibit a large-scale set of intelligence? And I think we all would have to agree yes. So then the question really becomes, okay, at what point is a robot intelligent? Moreover, what makes a robot, right? That's kind of, you see robots, there's some of the ones that I've done on the screen. That little orange guy is this one right here. This is a reference design that I do for my 404 robotics class. And a couple of other models that I'm working on too. Now these are the robots that we know, right? Wally. The Kuka arm is the one in the orange. That thing is, not Kuka, it's a Puma arm. Is there a laser pointer up here? No? Okay. My mouse died, so I don't have it.
No. Anybody have a laser pointer on?
They took them away once I started shining at the air. We have R2-D2, we know all that one. In the top corners, I mean, those are fictional robots, but we say, oh, that's a robot. Why do we say that that's a robot? The one in the orange, we go, yeah, looks like it probably makes cars. Is it a robot? I don't know. The one over here, Sojourner or Curiosity, one of those Mars rovers, right?
It's MSL.
Okay, which one is it?
It's the Mars Science Lab.
Curiosity probably says so on there.
It's Curiosity.
It says
Right,
it.
yeah, curiosity, spirit of opportunity.
So there's Curiosity, if you're curious. Clearly a robot. We say, yeah, it's a robot. How about the one on the left?
That's a robot.
It's a robot. Doesn't look like a robot, does it? I don't know. You know,
Is that one a
maybe-
robot or is that one RC?
What's the difference?
Well, if it's direct human control of every action, then it's not a robot.
Good question. So there's this thing called telerobotics. And I would argue that that in fact could be Curiosity. See, JPL sends commands to Curiosity, go here. In fact, they don't even tell them to go check out, if they want to go look at that rock, they don't say go look at that rock. Let's go a little bit towards that rock and make sure we don't run into anything. Okay, let's go again and drive the robots. They drive the robots from JPL. Imagine you spent $20 billion making a robot. Do you really want that thing to run around on its own and you had bad programming? I don't know. So again, that brings up a really good question. Does that one a robot? Is Curiosity a robot? Pizza's here.
Did get Little Caesars. That's unfortunate. Whatever.
So, while you're getting your pizza, I want you to think about this for just a brief minute. Why do we care about having robots? So what?
We usually have more than just cardboard.
That's all right. So go get your pizza real
We have
quick.
pizza instead of cardboard.
I swear this is the first time it ever. Because that door put you put it down.
Hey, Justin.
The tasking you with guarding.
Hey,
Badge hack this year.
Yeah, look. I'm glad.
I can't enter. Well, I put my pizza there once. I reviewed the schematic plan, so it's not
Everybody has the schematic
I had it for 2 weeks.
Yeah.
It wasn't fair. Like every year I had it's considered like I'm not staffed.
You get a lot of
Okay. So now we don't have to
this year.
Oh, why is that? I'm gonna give you guys a word of advice. When you graduate, when you have to have meetings, if you're gonna have a big, intense meeting, you don't want a lot of feedback, do it at 11 o'clock. Now, if it's gonna be more than an hour, do it at 1. Why? See, if it's, you wanna keep it compressed, people are sitting at 11 o'clock, so let's just get it done, let's get it done. If you do it at 1, it has to be a long meeting, everyone just came back from a big lunch, they're asleep. So, 10 o'clock, no. 9, no. 11 and 1. No, I'm just kidding. Okay, so, why do we want to build robots? I mean, why are we talking about it? I mean, who doesn't think they're cool? Yeah, really? That's what I thought. I mean, everybody thinks a robot's cool. I mean, who doesn't want to have Rosie cleaning your room? Because I know what your room probably looks like. It's college students. I mean, who wouldn't want to have a robot? We use them all the time now. When I was your age, we had hardly any robots being used. We had mostly factory automation robots, and that was about it. So, again, do we want to have solutions that look for problems, or do we actually want to be smart about it? And if we want to be smart about it, we really have to understand what it means for a robot to be smart. Now, that's a very good question, is what does a smart robot mean? Smart robot, the robot's smart. The robot is not born smart. The robot is smart because of designers and because of people who write code. Basically, you guys in this room. So, what makes a robot smart? I don't know. We're going to figure that one out. Why we need them? Other than the fact that they're cool? I don't know. What's our return on investment? We're not going to see a lot of robots used until we see a return on any kind of investment on it. There has to be a business case. So, what's the return on investment? We saw that in factory automation. Makes a lot of sense. But these cool looking mobile robots, let's face it, Roomba was a toy. And anybody who thinks otherwise is denying themselves the truth. It's a toy. But I'm going to argue that there's some very good applications for it, once we know how to write the code for it. So what is a robot? It should sense its environment. It should move. How should it move? I don't know. Should it roll? Should it walk? Should it sit there? If a robot that sits there and does everything but move, is it a robot or not a robot? What's the quantifications of what a robot is? Does a robot have to react to stimuli to dictate its behavior? It's a good question. So, if we see all these things, and you know, a washing machine's a robot by some of those definitions. So I think we would all think about that going, no, a washing machine's not a robot. It sits there. It moves, yeah. Does it move in its environment? Maybe. It's off kilter and like, well, I mean, that's a good question. So what is the key features? What are the salient features of making a robot a robot? You guys are all smart. What's a robot a robot? When we see it, we say, yep, those are robots. Washing machine? No. Why? Why is it we say one is and one isn't? Well, some of the elements that come to mind of what includes robotics is a mechanical system. It's an electrical system. There's a computer probably in it, although some guys from Beam Robotics might argue that one. Software? Yeah. But even having those elements alone don't constitute a robot, even if we had sensors in there. Okay, intelligence. We're getting somewhere. Intelligent system. What's an intelligent system mean? Well, there has to be controls in there as well. So all the engineering majors, you recognize when we see controls, first word that comes to mind when we see controls is what?
Feedback.
Exactly. We have to have feedback. So if we start looking at that, we understand there has to be feedback that it's going to interact with its environment. It may modify its programming, or maybe it's going to modify its actions based on the current state of its environment. And when we start talking along those directions, now we are going to begin to have a semblance of what an intelligent robot might be. But before we get into that, let's go ahead and define what the layers of what a robot would include. So, a robot is based on mechanical systems. The robot has several layers. We're going to cover them real quick. But underlying a robot has to be physical. It's the skeleton. It's the structure. And if we forget about that, then we just have a computer sitting on the desk. Which you might ask, well, was that really a robot or not? You could have a virtual robot, you could have a virtual machine, you could have a simulation of a robot running behavior. But let's face it, that's a simulated world. We're maybe 80%, because our simulations are never going to be real world. This floor is not level. There's bumps and stuff. Even if you exclude those floor plates, you're going to have bumps. Your simulated world, you're going to be hard-pressed to find that. So we have to deal with the real world. So as a robot that's maybe virtualized on here, the robot, probably not. However, what if I had a robot right here, some mechanical structure like this one, it was controlled by the laptop. The laptop's sitting on the desk, but the robot's moving around. Where's the robot at? Is the robot the mechanical system? Is the robot the computer? Is the robot the combination of the two? I don't know. I don't know. These are questions a lot of people are asking. I don't think there's any clear-cutting answers yet. But there's several different types of systems. There's drive systems that have 2 to 6 wheels. They fly, they swim. They all have to worry about size, weight, and power, because a robot can't take its extension cord with it. So you have to worry about endurance. All those things are we have to consider when we design these things. But if we move up the next layer, once we have that physical structure defined, we have to understand how we're going to move the robot and how it's going to sense its environment. So we have on this robot 4 independent wheels, and then there's a plethora of sensors that are up on top right here, camera, some sonar, and there's even some sensors that measure the internal state of the robot. That's how fast this robot's going by using some feedback from the encoders on here. So we have to have that. So we have to have that actuation, we have to have the acquisition layer of any robot. As we move up in that pyramid, we have to have more than just motors, we have to have more than just sensors. Somehow we have to have some low-level signal sensor processing where the robot's able to say, okay, the wheel encoder tells me it's going so fast. Just having the wheel encoder by itself is not sufficient. We have to use some level of processing, some level of controls in there. But even at this point, when we have our sensors, we can use some very simple sensor processing, that is, oh, something's in front of us, or I'm going so fast, that's still not going to be enough. We have to have some low-level controls, and when we do that, we have to have feedback. If we don't have the feedback, we call that open loop. The robot can run into the wall, and they'll just keep running into the wall, keep running into the wall. Not a very smart vehicle, would it be? So, some very simple logic on these switches. The switch, in fact, would be a sensor. The motor would go in here, and as soon as it's running, if it runs into something, it backs up. And then it goes on its merry way. When it backs up, it backs a little bit different. It actually starts to turn to the side. Very simple behavior, but it still has to have that feedback. Now as we move up, we start talking about a little bit more technical problems, and these are where it gets real interesting. When we cover 404 for robotics and electrical engineering, we cover up to this point on the pyramid. This is not trivial by any stretch of the imagination. This is your basic undergrad work. Where we finish up at this level is, suppose I have more than one sensor like I have on this robot right here, where I've got some sonar sensors and a camera sensor. I have to figure out which sensor is telling me the truth, because I guarantee you they're going to lie. This one will say one thing, this one will say something else. They're not going to be the same. So how do you differentiate which sensor is correct? What kind of algorithm do you need to implement to make an intelligent choice about what action should be taken? And I say those words very carefully, because when we start asking those questions, when we start looking at those implementations, that's when we figure out what robotic intelligence is. We can't ask those, we can't have a smart robot without asking those questions. There's a variety of different algorithms here. The computer algorithms we're talking about for these higher level controls, fuzzy logic, you might have all heard about fuzzy logic. That's probably another great topic that if you haven't had somebody talk on that, you should, in my opinion. Kalman filtering, it's an advanced algorithm as well. Any number of these things that are on here. When we go up from there and we start talking about autonomy, everything we've had up until this point, the robot's doing telerobotics. We tell it where to go. It's an RC car. It's a glorified remote control vehicle. What we want to do is have this robot think on its own. If it's going to map a room, it has to figure out how to map its environment. Now we're starting to talk about some level of autonomy. But maybe it has to do path planning. CS majors in here, you know about A-star, D-star, right? It's path planning. If you don't know about D-star, it's the online version of A-star. That's how a robot's going to figure out how it goes from here to there in the most optimal format. Now we start to say, okay, yeah, it's smart. It's figuring things out. It's figuring things out based on our algorithms, but what we want to do is provide it a framework that it can operate within. So we want to give it a box that it can live in. That's what our algorithm should do. How well we define that box is going to be how intelligent our robot really ultimately is. The other thing a robot's going to have to do in an autonomous environment is it has to realize that if the robot maps this environment here, and then all of a sudden some guy puts a chair here, the robot has to navigate around it. And come here, oh, there's a chair here. Uh-oh. I can't do what I was going to do before. So it has to be able to adapt to its environment. So we start talking about words like adaptation or adaptation. We start talking about planning, knowing which is more optimal, perhaps. Now we start to have a feel for what a robotic system is that's intelligent. Not just teleoperated, but actually has some knowledge of what to do correctly. Once we have an idea of what autonomy looks like, now we can talk about behavioral autonomy. So everything else was just autonomous processes that could occur either concurrently, that is simultaneously, whether you want to use multiple threads, multiple processors, however you want to handle the distributed processing that takes place on a vehicle, they contribute to a set of behaviors. Where these behaviors, when composed together, we start to talk about a robot that can perform navigation, exploration. To talk about exploration, you have to do path planning, obstacle avoidance, you have to do maybe dynamic route projections. But the problem we have is, although they should be task-oriented operations, how do we program these behaviors? Anybody who spent any time programming, we know how to write imperative code, don't we? If this is this, then that, do that. If this, then that, if that. We can do that all day long. How do we write behaviors? Moreover, how do we write multiple behaviors simultaneously so that they can interact, but still be autonomous and atomic on their own level? And there's a big challenge. Well, once we know how to do one robot, well, there's no fun in that. Let's put a whole bunch of them together. But if we already discussed the fact that writing a single robot level of autonomy is hard, how do we write the code to do more than one robot? That's a huge challenge. This is the state of the art. Now, the last thing we're going to do is, there's a break in that pyramid because honestly, we don't know how to get to pure artificial intelligence. We don't know how to get there. That's going to be the holy grail that we'll never get. We might approach it someday asymptotically, but I don't think we'll ever achieve it because it's just too big, too broad of a statement to understand what that means, because we have to understand what the question is, or we have to understand the definition of the word intelligence to begin with. There are a lot of people who are not very intelligent. So, you know, we can't figure out how do we write code to make figure that out. But that's the holy grail. That's where we want to get to. So what is robotic intelligence? There's more questions than there are answers for any of that. Our understanding level is over here just a little bit. We understand a little bit of it, but the complexity is greater as we move up that pyramid. Although the pyramid gets narrower, the complexity gets greater. So it's an upside down triangle at that point. This is an example of what a robot architecture might look like. It's similar to the one that's running in this robot right here. I'm not going to dwell on that, but it's going to be an idea of that's what it might look like. We still take an engineering principle approach. We break it down, we decompose it. It's top-down design, it's bottom-up implementation. So we have to start with some kind of an architecture. But the question is, so how do we write a program? I mentioned C#, some of you guys perked up. Now, some might argue that we program the physical layer with nuts and bolts. And I think that would be a valid argument. Maybe the level of acquisition and actuation, we start talking about soldering wires up together, maybe making circuits. Low-level controllers might have some simple microcontrollers. We write some C and some assembly using imperative methodologies. But once we get above maybe the full processor where we would have the high-level controls and the sensor fusion, we may no longer be able to write using imperative methodologies. We actually have to use some declarative approaches. Who understands when I say imperative versus declarative? Okay, kind of fuzzy. So imperative is what you would write in your C code. Okay. You guys all take C before? Most of you all written in C or maybe Python. C#, maybe. That's imperative coding. Declarative coding is a little bit different. Declarative is really more what you would consider a state machine to be. More data-driven. You declare the operations, and you describe how to respond. When we start talking in that way, now all of a sudden, things like high-level behavior abstractions start to make sense. We can describe a state machine. We don't even have to worry about its implementation. Now, if we have a state machine parser or a declarative design parser, now we're really talking. The thing is that does not exist very cleanly at best. They do exist out there. I mean, you got workflow for Windows. A little dicey there, especially if you like to write XAML code. But there's not a lot of good parsers out there. That's kind of where we need to be at, though, to write high-level behavioral autonomy. Once we go above that one, perhaps as these things start working with one another, it's more of a neural net. So I'm not going to get into the details of neural networks. We could spend an entire hour just on neural networks. We could spend an entire hour just on declarative languages. But what I did list here was just some different things to consider when we start talking about multiprocessors. You know, what language do you use? C#, C++, I don't know. Could be either one. When we start talking about some communication protocols, declarative works really well because we write state machines of how things should communicate. State machines for TCP/IP, as you all probably know. TCP/IP is probably not the answer, but it's a good example nonetheless. What languages do we write in? When we get to multiprocessors, or we get to higher level of intelligence, Lisp, Prolog, something that's got a clarified predicate logic methodology surely should be necessary. But there's not a lot of good ones for those either, because how many people have heard of embedded Prolog? How many people have heard of embedded Lisp? It doesn't exist, does it? We're talking big computers that sit here and actuate a remoted vehicle. So there's a lot of work that we need to do. So when we talk about robot intelligence, we say, why aren't our robots intelligent? It's because we don't have any clue what we're doing at the top of that triangle. This is what you guys need to work on. This is what I'm trying to work on. So this is what we know well, imperative languages. If this is true, then do that, else do something else. But that becomes very daunting, especially if you ever studied fuzzy logic, how many if-then-else statements you're going to have. It's just incredible. You could have an enormous number of statements just to do 5 sensors, or five subclassifications per sensor, I should say. It's very difficult to predict the unknowns of the environment as well. So what we start talking about when we declare a lot of if-then else's, we almost have an expert system, right? If we do this, then you have to do this. If you do this, you have to do this. We almost have to declare, or I should say declare, but we have to define every possible set of combinations in those possible outcomes. And we tried that in the late 80s. They were called expert systems. Even fuzzy came into expert systems a little bit, but we found it was just too big of a task. The universal set of unknowns is unknown and infinite. We don't know what we're going to have to deal with. So we have to take a step back and realize, you know what, that's not going to work anymore. We have to really understand the high-level controls. We have to really tell the robot how to do something. Not, when I say how, we want to give it the boundary box. We don't want to say, do this, do this, do this, do this. We want to give it the option to do path planning. We also concurrently want to give it the option to do obstacle avoidance. We also want to concurrently give it the option to follow the wall, if that's better to map its environment. So where are we at? We want to be able to tell the robot to search a room, but we have to ask ourselves the question, what does that mean? What does that imply? It would be great for us to say, robot search room. What C code command gives me that function? It doesn't exist. Now it would be great declaratively to say, search room, if return results, on a state machine, stay in this room. So if I had a state, that said, stay in search room. Stay here, not find. Find what? I don't know. That's for you to figure out. And when we're done, maybe we're going to go on and do something other. We start talking about this one, this methodology. Now all of a sudden we're talking about declarative methods. Now we have an idea of search room, where search room is a whole bunch of other things. And moreover, search room, this actually could be a hierarchical state where we have a whole small set of smaller states that do something else, right? What does that look like? I don't know. But that's kind of what we're at right now. We're trying to figure out what this means using this approach. Once we know how to write the code for one robot following this, then the bleeding edge of technology of where we're at is, suppose we have all of these working together. How should they interact with one another? Not only do we have enough complexity with a single vehicle, let's geometrically compound that problem when we stick a bunch of them together. Again, how do we write that code? Well, one of the ways we can do this, and we saw that with these very simple little robots, is we could do what are called bug behaviors. Where bug behavior is very, very simple code. For example, we could do wall following logic, or just simple obstacle avoidance explore. Kind of keep track of where you were. Hopefully you don't bump into anything, but in the end you get somewhere. I'll show you an example of a simulation that does it. It actually does a very good job mapping. Cockroaches use very simple bug behavior. When the light goes on, cockroach turns around and run. That's it. Very simple. Light goes on, run. When it gets to a wall, follow it. Finds a hiding spot, stay in there, turn around, see if the light goes out. Waits until the light goes out and comes back out. And you can think of some very simple declarative methods for that could be implemented on a vehicle. Now, what we could do is we could take those very simple paradigms of sense and act and compound them so that they're all running concurrently. So I could have a very simple behavior do that. I could have a very simple behavior that talks about how to communicate with another robot. They run concurrently. I could talk about another robot's behavior where if it's light, it describes what that functionality would be. We're no longer in the imperative domain though, are we? We're more in the declarative domain. But again, the problem we're going to have is how do we write embedded declarative code cleanly? That's a hard problem. What we want to do is have these things run concurrently. The problem we're going to have when we do that, as I've just illustrated here, is the designer is going to come up with whatever they want. Where's the structure of how to do that? Now, for the people who are CS majors, this is ad hoc, right? Where's the proof in the predicate logic for first order predicate logic going to reside? How do I know if I'm a complete design? Doesn't matter. Right now, we don't do that. Right now, we come up with a state machine or some algorithm and this is what we're going to do because. And as you haven't realized, today's talk is very open-ended. It's really going to give you guys a direction of where you guys should go and would go and where the technology is going to take us, that is the future technology can swim. So this is going to be what you guys are going to face if you choose to go into something like this. But the question is, why did the designer decide to do this instead of that? These are ad hoc methods. We need to validate our designs. Just because it works, is that necessarily the best answer? There's necessarily no method of validating this approach. A lot of times what happens is we stick the robot out there, okay, let's see if it works, right? Try it, oh, that didn't work. Try another one, oh, that didn't work. Try another one, oh, that didn't work. Not a good use of time, especially when we start talking about maybe 5 or 6 robots running around. The number of variables are so high that we don't necessarily know if we're going to have enough coverage for a test case. So you guys talk about test-driven methodologies, right? Test cases, a lot of Microsoft has that built in now where you always write test code first, and then you write your body on top of that. Okay, well, how do we validate the dimensional problem that we have if we had 5 robots running around? It's a big problem still, right? Well, one thing we could do is we can actually set some rules to our plan. So we still have our sense plan, or sense and act, but now we have this plan box over there where we can set some guidelines. Now the plans are static, means they're not going to change. Maybe they should change, I don't know. But what we do is different rules are going to elicit different acts. These things run in concurrency, but depending on the current state of the environment, you might want to choose a different outcome. So what we could have is, in fact, is some kind of an arbitrator, that when we have a sense, plan, and act occurring, the arbitrator is really more of the intelligence in the robot. It says, if I have a given state, and believe it or not, this is actually what I'm doing right now. When I have a given state of an environment, I want you to take this set of behaviors. But when that cost function changes, I want you to use those set of behaviors. They all run concurrently, however. All of these things run. Now, the one question somebody might ask is, well, how does it adapt? Because one of the things that we talk about intelligence is the ability to adapt to an environment. For example, the chair is placed in the center of this room. How does the robot adapt to it? Especially following a paradigm that we see right here. Well, what we want to do is have what's called a weight table. And the weight table is what they're going to do is they're going to ascribe, or you're going to ascribe these weight tables of fitness value. How well does it fit? How well does it work? What's my feedback of the overall effectiveness of this particular algorithm currently being executed for the output function? Because remember, all of these things run concurrently, but only one of them is implementing the actuation. So the weight tables are going to allow us to pick based on the fitness functions of what's most appropriate based on the feedback. Everybody following that part of it? That's key. So we have an arbiter. That arbiter is really defining the intelligence for us. And believe it or not, this is what we're doing. I'm hungry, but I don't want to get up because there's no more pizza. Right? You're all thinking, I wish I had more food. That's going on in the back of your mind. I got to listen to this guy talk because that's really cool. I want to listen to that. Okay, that food, oh, it's not there. We are processing concurrent tasks simultaneously. We have a given cost function that we've ascribed a set of weight tables that's going to drive what we ultimately do through some set of norms. Either they're societal norms, or either innate norms or prescribed. You know, we all know about fight and flight. Something's going to set that off to us. So we have a set of behaviors always running, even though let the arbiter allow that to happen. Now the question is, how do we write that arbiter code? So far, sense, plan, act, we can follow through using this methodology. Arbiter can also be using this methodology, but we can also talk about some genetic algorithms where they arrive at solutions based on previous generations' fitnesses. We can talk about neural nets. So we do have an adaptation model that we can draw from for all those elements. Now, when we talk about all of these vehicles now interacting with one another, we need to talk about what's multi-agent technology. So we just got done talking about, let's just go back in. Talk about how a robot might work. Now, can we take these robots, define a set of behaviors of sense, plan, acts with arbitration, and then have several of them interact with one another? Because, let's face it, a robot working by itself isn't very smart necessarily. How many of you guys played sports, at least once in your life? Probably everybody, right? When you have a 5-year-old playing soccer, what do? They all chase the ball. They all run the same algorithm, don't they? Yeah? No interaction knowledge whatsoever. Okay, let's progress now. Soccer's a great example because that happens. In baseball, they all kind of chase the ball, but they have designated spots, a little bit more so than soccer at that age. When they get older, they have positions, right? Maybe you have a sweeper, midfield sweeper, maybe you're playing a 7-man type of rotation, you have your forwards, you got your wings if you're gonna play wings. You have a set of positions, and the intelligence is not only in the prescribed algorithms for that position, which you could have, but let's just suppose everybody was running their own prescribed algorithms. I'm a center, or I'm a midfielder, okay. I'm going to kind of go up, maybe assist, and come back, ball's coming back, I got to sweep across the side. If all I did was follow the ball, would I be a very good midfielder? No. I got to set my forwards up, don't I? I have to see where my defenders are at, if they're going to be able to come back. Maybe I come back behind my defenders and back them up, instead of attacking the guy coming down on me, right? So I have to have a knowledge of my neighbors. The interaction is more key, or is as key, as my individual behavior. So when we start talking about group and multi-vehicle intelligence, not only are we looking at simple behaviors that define the roles of the individual robot, but we have to understand the interactions. Then we have a group intelligence. Then we have some robotic intelligence. Because if the robot can't interact with its environment, which are its neighbors, it's not very smart. These neighbors are time varying, aren't they? They are dynamic in the static environment. So the robot, as I said before, has to be able to interact with its changed environment. However, quite often, those elements that are changing are other vehicles themselves. So we get a really interesting paradigm. But it turns out we can see some very simple solutions for that. You guys have all heard of Boyd's, which is what I have up here on the screen. So Boyd's was written by a guy named Craig Reynolds back in the mid-'80s. Because he was a lazy programmer, didn't want to write a bunch of individual birds flying around. What he was able to demonstrate, I'm just going to skip to that. What he was able to, only go back for a minute. Come back to that. What he was able to demonstrate is using some very simple behaviors, he can have an emergent overall behavior occur. That's very big. When you look at a soccer field of several players, those players, they're not all the same type, are they? So we consider that to be a heterogeneous composition. They're all doing something different. They have a different motivation to implement their actions, but they have an overall driven goal. We can also talk about homogeneous systems where all of them are the same. When we talk about homogeneous systems, then we start talking about swarms. We talk about flocking. We can talk about the predator-prey algorithms. Therefore, predator-prey, we might have two types of vehicles. What we'd have up here would maybe be one species here, maybe a slightly different subspecies. Very similar, but this one's a little bit better evolved for some terrain. This would be better evolved for a different terrain, wouldn't it? So they're similar, a little bit different. In popular culture, we've seen this a lot. In Michael Crichton's Prey. I don't know if you guys have read that book. I do recommend it. It's a little bit out, it's not out there, it's still old, probably about 10, 15 years old, but read it. Good book. And then of course we have NBC's Revolution. It's kind of a fun take on that too. If you haven't watched it, it's kind of funny watching them talk about the technology, but it's out there. So when we talk about these multi-agent systems, what we want to understand is something that's called agent-based modeling. Because what we're doing right here is we're modeling the behavior for a given agent. And if we can understand agent-based modeling, we can understand the behaviors that are associated to that using declarative methodology. Now all of a sudden, we can start to put things together. And in a very simple example, here's the Boyd's model. Let's just go ahead and, I think it'll automatically run. If Cal Poly's internet's working, check that.
The internet died a little bit ago.
What's that?
So the wireless in here died just a bit ago.
Oh, nice. Okay. So anyways, you can check that website out. You can Google Boyd's, find all sorts of examples of it. And basically it's composed of three simple premises. We have separation, alignment, and cohesion. Where the separation is that the birds need to steer towards one another. They need to find friends. And by the way, just a historical note, how many have heard of Boyd's already? A few of you maybe? Okay. So Boyd's, you might ask yourself, why did they say B-O-I-D-S for Boyd's? Because in New York, they call birds Boyds. Did you not? So Boyds, the Boyds, for the Boyds, they have to like each other. Okay. Now, here's a very interesting example. Just look in the room amongst yourselves. Just look around. If you don't know the neighbor next to you, you probably sat one chair away. Am I right? Why? Human nature. It's natural for us to do that. We want to be close, but if we're too close, I'm going to skip to cohesion real quick. If we're too close and I don't know you, I want my personal space. Nothing against you, but I just my personal space. Now, if he's my buddy, his name was fine, dude. We'll sit down next to each other. Well, that's a little different. So we have cohesion, but we also have separation. So we want to avoid crowding, but at the same time we want to like ourselves, or like our friends. Now, the other thing we have to worry about is our alignment, and that is we all kind of have to steer in the same direction. Right? If you guys started walking around somewhere, you guys can do this yourselves, walk over to the student union area, you guys would kind of cluster, you'd be close, and for the same reasons, there might be a separation of a chair here, you'd have a little bit more of a gap walking over there, and if you're really good friends, you might be a little closer. It's just the way it works out. And that's what these three very simple behaviors, and we can identify these behaviors. The code for this is very, very simple. And I do have it running on here somewhere, so if we do have time, I can pull it up. But that's boy, it's a very simple example of distributed swarm behaviors based on more of a model here, though we write it using some imperative coding methods. Why do we care about using this? Well, we can do mapping. We can map systems. So if all of a sudden each robot was following a Boyd's model, but it was keeping track of where it was at, it was mapping an environment, I don't have to tell each robot how to do its job. I give it the framework. I give it the large box to live within, and I say, go do this. Maybe I want to do search and rescue. And if I have a UAV that's got a gun on it, I'm going to have it destroyed. It's not beyond the realm of possibility anymore. We could have a fleet of drones running around shooting things up very easily. Search and rescue and search and destroy are almost the same algorithm. Very simple algorithm at that too. Traffic system modeling, that's where I'm doing my stuff right now. What I'm doing is I'm looking at a bunch of cars being autonomous Google cars, for example. And the problem is, as you guys all know, if you're on the freeway, there's almost always traffic, right? And depending on the time of day, that traffic quite oftentimes is maybe caused by an accident. Because there's so many people on there, they're all right into each other. And they cause an accident. So the next question is how do I get around my accident? How do I get around what it is I need to go from point A to point B? I got 5 minutes, right?
Yeah, 7.
7. Good. I'm on traffic. So you all say, I know, I'm going to get off at the next, if I'm going on 91, I'm going to get off and I'm going to go down maybe Santiago or maybe I'm going to go on La Palma, right? The thing is not only did you have that great idea, but so did everybody else. So everybody says, hey, we're all going to go do that, and all you did was move traffic to the arterial roads. So what I'm working on, this is my research, and it's been very successful, is using methods like this, using heterogeneity to my advantage. Every vehicle may have a slightly different purpose and or type of vehicle. So I have those vehicles making decisions based on the type and a lot of other little characteristics that we talked about. And by using some simple algorithms, I've spread out that traffic so that there's no more delay. It may be a suboptimal solution for the individual, but it is the overall optimal solution. So we can apply very simple principles to some of those types of problems. So here's a real quick mapping. So here these vehicles are just kind of running around and they're seeing stuff. You can see their sensors are right here. And then the one above that, you can see the map that they're actually generating. Is it necessarily individually optimal? No. But is it overall optimal? Yes. Now when you stop and think about watching these, how much different were these little robots down here behaving like this? Not much. Okay,
What framework is this?
oh, I forget. I didn't do it.
So they're detecting collisions with each other.
Yep.
They actually recognize the collision with one another, or?
Yes, they do.
That's all that black stuff.
Well, I guess what I'm trying to say is, do they recognize the individual ones? Do they
Yes.
recognize
Yeah, you have to know you're a robot versus a wall.
Okay.
You have a return to. It's like watching the Three Stooges, right? But imagine for a minute, I mean, this is really no different than watching ants on the ground, or sawbugs, right? They're very effective, very simple behavior. So again, does a robot have to have complex code to be intelligent? No. It has to have well-written code to be intelligent. Where'd they go? Now, these are using non-communicative algorithms. Imagine if these robots actually communicated with each other, which is possible. You probably have a higher degree of efficiency of implementation. I think this is the last one. Oh, nice. Restart. Okay. Now, here's another application. This was done in Europe. The other one was done in the United States. This is it's just kind of scary, actually. I don't know what professor would ever do this to their child. Imagine you had a bunch of robots that you decided to do some search and rescue with. I think is kind of the idea that they're showing. So notice she's holding it in the hand, right? Mom, please don't let him get me. So let me speed it up real quick. I think that needs, no, I think we do it faster.
Good incentive to have a child.
You have to do anything at the top.
No, you can click there.
That's really fast.
What's interesting is actually they're communicating with one another, and they're illustrating using those little rings to show the current state. So they're changing states, they're adapting, behaviors are running concurrently. These robots are smaller than this one. It's probably somewhere between these two. Just to give you an idea. Any robot by itself could not pull a little girl. But you put a whole bunch of them together. But that's not the point of the video. That's a different one. So, where's the intelligence at in those? That's a good question, because it could be the group, it's the swarm, right? Where's the intelligence? You could simply say that each one of those are processes. Okay, so you have processors with subprocessors in it. That's okay. I'm going to go ahead and skip this one. This is kind of where my research is at. And if you look at this, you spend some time looking at it, this does what we needed to do. This is the model that I'm using to not create an ad hoc behavior and to allow for vehicles to interact with one another in a pre-described method with some semblance of thought to it, not just being ad hoc. So this is some really cool research that's going on right now. I have a paper that I just published and should be presenting hopefully in the next couple of, probably at the end of summer. So this is getting some pretty good news. So where are we going? It's up to you guys. It's really up to you. Questions?
Guys, we're actually out of time, so, if we could,